Hi, this is a presentation on triangulating the results of qualitative comparative analysis. It's about the use of decision tree algorithms to visualize complex causal models and to identify alternative causal models to those found using qualitative comparative analysis. How do QCA and decision tree methods compare to each other? They have two similarities. They use the same kind of data and the results of their analyses are comparable, but the way they do their analyses are different. I'm not going to go into the details of those during this brief presentation, but I can explain more after this session. This is the kind of data set that can be analyzed using QCA or decision tree methods. In this case, it is a data set taken from a paper on QCA by KROOK, who looked at the levels of women's participation in parliaments in 26 different African countries. In this data set you can see the 26 countries listed down the left hand side, row by row, and across the top you can see the first 5 columns describe different attributes of those countries which the author thought might be associated with different levels of women's participation in parliament. And on the far right column is the percentage of women in parliament. Now the data here is in binary form, so the attributes are simply described as being present or absent using a 0 or 1, and the percentage of women in parliament is summarized as being high or low, again using a 0 or 1. Behind this data set, of course, is quite a lot of coding work that has to be done, which is quite time consuming and has to be done with care, but I'm not going to be discussing that. The point is that this sort of data set, although it's generated by QCA analysis or in the process of doing QCA analysis, can also be used by decision tree models. What can QCA results look like? They are typically expressed in the kind of formula that you can see at the top of this slide, which can be interpreted or read as follows, and that is that high levels of women's representation in Parliament exist if quotas and a post-conflict situation exists in a country, or there's a high level of women's status and it's a post-conflict situation, or quotas exist and there's a high level of women's status and a high level of development. You will notice that the and signs in the formula actually mean or, and the multiplication signs actually mean and when translated into normal English. Not exactly a user-friendly representation, but it's one that you can get used to. And this is what a decision tree looks like. It's an inverted tree with the root at the top and the leaves at the bottom. Each of the nodes in this tree describe a condition, to use QCA term, or an attribute, to use a decision tree term, and those attributes are the ones you've seen already: the existence of quotas, women's status, post-conflict situation, level of human development. And the branches represent configurations or combinations of those conditions. So you'll see on the right hand side there's a branch which consists of quotas and post-conflict situation. On the left there's a branch saying the absence of quotas and the absence of women's status. The leaves at the end of each branch represent the outcomes associated with each of these configurations or combinations of conditions. And the point to note here are these branches, the sequence of the conditions along the branch does not represent a causal sequence in the sense of one thing happening and after or before another. It just simply represents the combination of those conditions. At the beginning of the presentation I referred to complex causal models. So in what way can these models be described as complex? Well, there are a number of attributes which I'll spell out. The first is equifinality. In other words, there are multiple ways in which an outcome might be achieved. In the decision tree, there are 3 separate configurations or ways in which high levels of women's participation can be achieved. Secondly, this model is what you call a conjunctural model. Each of the configurations has 2 or more conditions. Conjunctural causation models usually have multiple conditions in any configuration. Thirdly, the causal model displays asymmetry. The causal configurations for high levels of women's participation are different, but not the opposite of those for low levels of women's participation. In the models which can be generated by QCA or decision tree algorithms, there can be different types of causal conditions present. There can be conditions which are necessary, there can be conditions which are sufficient, there can be conditions which are necessary and sufficient, and there can be configurations of conditions where a condition may be an insufficient but necessary part of that configuration, which itself is sufficient but unnecessary. These are called EES conditions, and every condition in the decision tree you saw a few slides earlier is in fact an EES condition. They are the most common types of conditions that we tend to find. Sufficient or necessary conditions, or necessary and sufficient conditions, are a lot less common. Another interesting point to note about the decision tree representation of causal configurations is that we can actually say something about the extent to which each condition has a contributory role relative to all the others. We can count the number of configurations that a particular condition contributes to, and I've just listed the counts here for the 4 different conditions, quotas having a bigger role than the rest. But we can also get into more sophisticated measures which take into account the number of cases associated with each configuration. And when this is done, you'll see that there's been an adjustment here of women's giving that a slightly higher contributing role than it had using the raw numbers alone. I'm now going to talk about how we compare QCA and decision tree models. The first 2 methods should be familiar to you. We can look at the internal validity of the models and the external validity of the models. To look at the internal validity of the models, we need to look inside the individual cases for evidence that there are causal mechanisms at work which are connecting the conditions which we've found to be associated with a given outcome. The proposition here is that in order to have a plausible claim of association, we need both an association and a mechanism. In other words, associations are necessary but not sufficient. The other way of comparing the 2 types of models is to look at external validity. Can the results be generalized? Decision trees almost always get tested against a separate data set, usually a section of the original data set that's been held back. With QCA analyses, these are rarely tested against additional data, not because it's not possible, but I think possibly because it's largely to do with historical data. However, when you look at the KROOK data set above, it would be quite easy to test that against other data. For example, the status of women in other African countries outside the set of 26 that were studied. The third way of assessing the comparative performance of the 2 types of models is to look at the internal dimensions of the models, and that's what I'm going to focus on from now on. There are 2 dimensions of these models. One is their simplicity or parsimony, and the other is accuracy. And simplicity we can measure in a fairly simple sense of just counting the number of configurations needed to account for all outcomes, and also counting the number of conditions in those configurations. Accuracy can be measured by looking at the proportion of all the outcomes that are correctly classified by the model. In QCA terms, this is referred to as consistency. A point to note about these 2 dimensions of performance of the models is that these are often competing requirements. I'm now going to apply those criteria to 2 sets of data, one which you've already seen, which is KROOK's data on women's representations in Parliament. The QCA analysis generated 6 configurations using 4 of the 5 conditions and had 100% consistency. In other words, there was no classification error. With the decision tree model, there were 7 configurations, the same level of consistency using the same number of conditions. So a small difference, 1 more configuration than used by the QCA analysis. Here we have the decision tree that you saw earlier, and under each of the configurations I've put the Boolean algebra expression of the QCA configuration that corresponded to the one found by the decision tree models. Basically, there's a very strong correspondence between the two models. There is only one difference between the 2 models. In the QCA model, there was 1 configuration which said that low levels of women's participation will be found where women's status is present, but it's not a post-conflict country or situation. However, those 2 cases, when we look at the decision tree model, they fit under 2 different configurations as shown by the arrows here. In one case, that the country concerned is where there's no quotas for women, and in another case it's in a situation where there is quotas for women. So the question then is, how important is that extra condition of quotas? And the way to find that out is not at this level of analysis, but to look within those two individual cases in detail to see whether there was an argument for quotas actually having a significant causal role in the outcomes that were observed there, or the absence of quotas having a significant causal role. The next case I want to look at is a recent review of evaluations on the prevention of violence against women and girls, and here they had 39 cases of evaluations, and they were looking at 9 conditions that might explain whether the evaluation was effective in having some effect on policy or people's understanding and practice. And in this case, the QCA analysis produced 8 configurations for positive outcomes, whereas the decision tree model produced 3 configurations for the positive outcomes. The levels of accuracy or consistency were almost the same, with the QCA model being slightly less so. The QCA model made use of 8 of the 8 conditions, whereas the decision tree used only 4 of 8. So there's quite a dramatic difference between these two models. So here is the representation of the results of the QCA analysis. They're not in the form of the algebraic expressions, Boolean algebra expressions that you saw before, because the authors were experimenting with a different form of representation. The 8 configurations are shown as separate bars, and across the top are the different configurations which are represented in each of those configurations, with dark cells representing the presence of those and grey cells representing their absence. The interesting point about this result is that the 8 configurations have a coverage of 186% of the cases. In other words, there's quite a lot of redundancy. Some of these configurations predict or explain the same cases. In fact, there are 2 ones which I pointed out which could be removed from the model altogether because they are covered by the other configurations. But whether they're the right ones to remove is an open question. That would need to be investigated by looking into the cases which are covered by more than one configuration to see which configuration offers the best causal explanation in those particular cases. This is the decision tree model using the same data set. As indicated earlier, this model is considerably simpler. There's only 4 conditions required. There's only 3 configurations needed to explain the positive outcomes, another 2 to explain or identify the 2 negative outcomes. The important point about this model is that while it's good at identifying positive outcomes, there's a 96% accuracy, it's quite poor at identifying the negative outcomes, a 36% accuracy. We don't know the performance of the QCA model because they didn't analyze or identify configurations that were associated with negative outcomes. So the question here is, while we've got a nice simple model, whether this level of accuracy is sufficient for the purposes needed or not, and whether a more complex model might give us more accuracy. This is another decision tree produced using the same data, using an online service called BIGML, and this decision tree is more complex. It's got more branches, and in this case there are 16 configurations which explain the same number of outcomes. Even though it's a more complex model, the overall accuracy is somewhat less at about 80%. There's been an improvement in the identification of negative cases, up from 36 to 54%, but a fall in the accuracy of positive cases. So more complex models don't always deliver more accuracy, although generally that might be expected. So looking back at these examples that I've shown you, what are the ways forward? What can we do when we compare the models produced by decision trees and QCA using the same data sets? Where the differences between the two models are small, it seems that within case investigations of the causal mechanisms at work and the differences between the two models is feasible and an appropriate thing to do. For really big differences, it would seem more useful to rerun the analyses using the simplest set of conditions found by the two models, and to see whether the 2 different approaches will generate the same results when using the same 2 reduced set of conditions. For models which have low accuracy, we may want to develop more complex models, but they may not always deliver, as we've just seen. For models with high level of complexity, we may want to simplify them, but the question then is, will that reduce the level of accuracy or not. And when we can't find the satisfactory combination of level of accuracy and level of simplicity, it may be because we simply don't have the right set of conditions in the database, and that we need to go back to the data set and think about the inclusion of other conditions, which when new models are created will have a better combination of simplicity and accuracy. This last slide is a reminder of why it's useful to reanalyze existing data sets. There's a lot of evidence to suggest that reanalyses can generate either very different interpretations of the original data or improved understandings of the existing interpretations of existing data.